And then we have our last talk of this session, which is a remote talk. We have Daniel Goodman, who's at Oracle Labs, and he'll be talking about Sandwood, Runtime Adaptable Probabilistic Programming for Java. Do we have Daniel on the remote connection? Yep. Yeah.
Today I'm going to talk about Sandwood, which is an open source Java-like probabilistic programming language from Oracle Labs. Unfortunately, I can't be here in person to present today, but online to answer questions at the end of the talk. Many of you will already be familiar with the idea of probabilistic programming, but I'm going to do a quick recap for those who've not come across it before. So probabilistic programming is a way of constructing Bayesian models. Bayesian models are a form of machine learning model where the model is described in terms of the relationships between random variables. These relationships are expressed by the programmer based on domain knowledge they have of the problem they're trying to solve. Because the model is constructed with domain-specific knowledge about the structure of the problem, they have a number of advantages over solutions such as deep learning. The known structure means the model is more explainable. Also, because the structure doesn't need to be learnt as it does with deep learning, it requires less data and so can work on much smaller problems. And this reduction in size reduces the latency and the cost of training the models. So that's Bayesian models. Why use probabilistic programming? Well, often it's relatively easy for a domain expert to write a model that models the problem they're trying to solve, but actually implementing that so a computer can do the required inference, etc. on it is much harder. So you'd have a description of the model in the comments, and then some inference code that's going to be used for training, and some further inference code that's going to be used for making predictions, and all three of these pieces have to be kept together, and the inference code is considerably more complicated than the overall structure of the model, and all in all this just becomes hard to maintain and hard to work with. So the idea behind probabilistic programming is to raise the level of abstraction and to have a simple language that instead of having the comments, we write the model in this higher level language, and then we use tooling to construct all the required inference code. This greatly reduces the cost of implementing and maintaining Bayesian models. Sandwood is far from the first probabilistic programming language. Its immediate predecessor within our group was Argo, which we developed in order to demonstrate that we could compile probabilistic programming languages and run them on GPUs. This time around we wanted to produce a language that was more robust and more mature so that we could actually use it inside of our products. It's designed to be familiar to Java developers so that when they look at the models they understand what's going on there and you don't end up with black boxes within the products that people don't want to touch. It's got compile time checking so that we don't end up with runtime errors that are unexpected. It's designed so that the models will form discrete components of the system, so unlike APIs which are running in a host language where you end up with potential for merging between the API calls and the control logic. With this we wanted to make sure that the control logic that affected the system's behavior based on the results from the model was separate to the models themselves. And we wanted the ability to target multiple different pieces of hardware as the operations change. So for example, you might want to run on a much larger machine when doing your initial inference versus when you're making predictions later on. Currently Sandwood can perform single-threaded execution, fork join execution, and can run on Callisto, which is an internal runtime system developed by Tim Harris. In the future we want to move on to working with the Java Vector API and to get back to where we were with Argo, running on GPUs. So what does a Sandwood model actually look like? Well, this is a hidden Markov model written in Sandwood. Please don't try and read all of the code now, the slides will be available later for people who do want to go through this. But the point is that this is very much like Java code, and so it should be very familiar to Java developers. The random variables are represented by objects, which have a method sample attached to them, and these objects are instantiated either by a call to new or by the use of a factory method as we're doing here. Points where Sandwood models differ away from Java are things like the variables are all single assignment, you can't call arbitrary Java functions, and unlike a Java class which takes no arguments, the models take an argument using a constructor syntax very much inspired by Scala and therein our earlier work with Argo. So having written the model, the compiler pipeline for it looks something like this, of which the bits that are of interest for this talk are the first 4 steps. So we start off by doing a source-to-source translation to a set of Java API calls, and we then compile the resultant code and execute it in order to build a DAG. By doing this step, we're able to take advantage of the Java compiler for the type checker, so we don't have to write a type checker ourselves. Having constructed the DAG, we explore it for all of the variables that are of interest and all of the possible traces between these variables. Having gathered all of this information, we then use that to construct the various inference methods required by the model. The output from this pipeline is a set of classes that represent the model. These include a class with the same name as the model, When instantiated, this object will be the object that the user interacts with in order to control the model itself. This object will have fields for each of the named variables within the model. These fields reference objects which can be used to get and set properties of the variables within the model. In addition to the publicly visible fields, the model will also have a private field referencing an object that performs the arithmetic operations required for the model. This object can be changed to target different hardware, with the relevant state being copied between the objects as required. We'll now look at one example of how this model might be used. So in this example, we're going to infer some of the values within the model based on some observed data. So the first step, of course, is to get the observed data, and where this comes from is entirely up to the user. Having got the data, we then instantiate an object that represents the model, and if we want to have multiple copies of this model, we can just have multiple objects. Having constructed the object, we can then set the retention policies that we want for the variables. So we want to record the most likely values for the variables within the model. So we're going to set the default retention policy for the model to be map. But in addition to this, in this occasion, we've decided that we don't want to record all the possible states that the model goes through. So we're going to set the retention policy for that specific variable to be none, so that those variables just get ignored and don't get recorded. Having set up the retention policy that we're looking for, we can then just tell the model that we want to infer values for 2000 steps, and this will perform give sampling for 2000 steps, recording the most probable values that it comes across within this chain. Having performed this inference, we then record the most probable values from the variables within the model by going to each of those variables' objects and just requesting the map value from that object. So that demonstrates very briefly what a Sandwood model looks like and how a user might interact with them. We're now going to change gears slightly and look at some of the problems that were associated with creating Sandwood. So one of the issues is that it's possible to have much more complex relationships in a Java-like language than it is in other languages which are structured to prevent such relationships. A simple example of this in the HMM model is this piece of code here, which describes how the model moves from state to state as it transitions through a sequence of states, generating the sequence of events that are observed from this model. So what's going on here is we start off at t0 and we use a random variable to select a random state to begin in. And then based on the state that we're in, we will pick a transition to another state at time step 2. And we will continue doing this through all of the different time steps so that the model is steadily moving through a whole sequence of different time steps. The problem that we run into, though, is that the states are written in two separate locations. So when the states are read here, it's not clear which of the random variables that the categorical that's currently reading from the states is interacting with. Is it interacting with the categorical that picked the initial state, or is it interacting with the categorical that generated the state on the previous iteration? In order to handle this, it's necessary to build a set of checks and guards that will ensure that the code for interacting with each of the possible random variables from where the state could have come from is only executed if that is indeed the random variable that the state came from. And obviously this is a relatively simple example, but because this is Java-like code, these relationships can get arbitrarily complex. So how do we go about doing this? Well, we start off with the for loop that the random variable we're wanting to find associated random variables for is currently executing in. And this loop's going to have some code that's executed before we get to the point where we want to work out what's going on with other random variables, and it's going to have some code that's executed afterwards. We then, as we discussed, have a set of traces between all of the possible points in the DAG. So in this case, we're going to have two separate traces, one of which is a trace from state I-1 to state I, and then up to the categorical that generated that value, and a second one from going from state I-1 to state 0. So for this example that we're going to work through here, I'm going to look at the trace from state I to state I-1. So we have the ability to create variable and scope substitutions, and we can use this in order to explore all of the possible array indexes that might have been generated. So when we go back to look at the put into the array that happens at state I at this point, of course, would have had a different value to the value of I currently. As such, it's necessary for us to be able to explore all of the possible values of I. And so what we're going to do is create a new for loop that's going to explore through all of those possible values. And that for loop is going to have a different index name, and that index is going to be substituted in where appropriate as we work our way back up the traces, so that we end up with a whole loads of different scopes nested inside of each other, each of which have a different set of substitutions which are required to be made to the code, such that the code appears to be executing in the environment that the element in the trace would have executed within. As we work our way through then, we're also able to put in guards, so we know that if this trace is valid, then the location that the value was written into must match the location that the value was read out of. So I-1 must equal I1 for this trace to be a valid trace and for this to be the random variable that we will be looking at. If there's more than one trace between two random variables, of course, you can have more than one. You're going to have more than one set of values that need to be compared, and this is going to require guards to ensure that the code that ultimately gets put in the inside of all of these nested for loops and nested conditionals is only ever executed once. All of this adds a lot of complexity, which we wouldn't want the implementer of an inference algorithm, for example, to have to consider. So to overcome this, we abstract it away into objects called scope constructors. So we start off with a scope constructor for the outermost for loop, and then we'd use a lambda to add in the code that we're going to execute before we were interested in this relationship. We can then pass to the scope constructor a set of traces from the location that it's currently modeling to an alternative location in the DAG. And using these traces, the scope constructor will construct another scope constructor representing this new location. So this is now the target for code that we've got marked down at the middle of all of these for loops. And we can now add code to this location once again by using lambdas. And we can continue to add code to the existing location by passing more lambdas to the original scope constructor. And we can nest this arbitrarily deeply. And so the user never actually sees what's going on in all of this. All of this code is generated and output without the user ever being aware that it happened. They just say, I want to run this code only if there's a relationship between this random variable and this random variable, and everything else is handled on their behalf. People will of course have noticed that the big problem with this is that we've now gone from something that should be a constant time operation because we've only got one possible path to something that's going to take order n times to search through all of the possible indexes. And this of course will only get worse as we end up with more and more nested loops for longer and longer traces, with our execution time being exponential in the length of the trace. The good news is this code can be effectively optimized. So the first observation is there is only one value of I1 that will ever satisfy the guard of the conditional. So we can just declare I1 as that value, and instead of having a for loop, we can have a conditional that checks that the value of I1 is one of the steps that the for loop would have reached. Some of the guards within this for loop can then be removed, so the one that checks that we land on the appropriate steps is trivially true, and with some bounds checking we can get rid of the upper bound because that's also trivially true. So this finally leaves us with the option of substituting in the value of I1 into all the rest of the code. So we change the substitutions when we're updating the code, and we now have a guard that simply says that I must be greater than or equal to 2 for this random variable to be reachable. And so we've gone from some relatively complex, expensive code to something that's clean and efficient to run by applying a simple set of optimization rules. Going back to our HMM state transition model though, say we're at state 3 and time step 3. We may have got here by this path, but for a lot of the computations that we're going to want to do, what we really are interested in is the probability of getting here by any of the possible paths. And so that's added into Sandwood via the ability to say sample distribution. So we've taken the code that we showed previously, and now we've just changed it so that we're doing sampling a distribution instead of sampling a single value. This is applicable to all finite distributions within the language. The handling of sampling distributions relies heavily on the ability to detect relationships between random variables and is included within the abstractions that mean that the users don't have to think about how all of this work is done. They just have to think about the inference algorithms they might want to write. So in conclusion, Sandwood is a JVM-based probabilistic programming language that's designed to be familiar to Java developers. It's able to adapt to different runtime environments. It outputs encapsulated models, which are clean separation between the model and the application code. It's open sourced and available at sandwood.org, and we are recruiting both full-time and internship roles, so if you're interested in one of those roles, please do reach out to me. Thank you very much, and I'll now take any questions if there's time.
Do we have any questions for Daniel? Okay, I have a question.
Okay.
I'm wondering, I've seen sort of similar things before, I think in the context of trying to do exact inference for discrete variables in Stan. In that project, we ended up trying to build vector graphs or DAGs out of our sort of imperative stand programs, which are somewhat similar to your Sandwood programs, it seems. And I guess the problem we run into then is that, if you have array indexing like you have in your HMM model, then you get that the structure of the DAG or the vector graph is only known at runtime. And we wanted to do everything as a compile time transformation, and then we couldn't figure it out. And I'm wondering, does your system handle these DAGs at runtime? And does that mean that you can really do things like a sum product algorithm or like an efficient exact algorithm on some vector graph or DAG representation that you derive at runtime by jitting maybe? Or
So the way we get around that is I seem to have an echo, sorry. The way we get around that is by having when we create the traces, we look not only at all the puts that have happened to the array before we got to our current location, but also at all of the possible puts that could happen afterwards in the array. So we actually end up, whilst it is a DAG, because it's got this extra scope information around the nodes, we're able to build a bigger set of traces than you would be able to get out of the DAG normally at compile time. And so normally you would end up at runtime having to get this extra information because you don't know how many times you're going to end up unrolling the for loops. But because we build these extra traces in of, well, this information could have come from later in the DAG, we're able to overcome that. The one limitation we do have on that, though, is you can do, for example, A0 equals A1 through N, but you can't set it so that without having a random variable in between for AI to be written into AI plus 1. So you couldn't just copy every element along in an array, because at that point you do have an unbounded number of for loops that you would need to nest within each other. But for that, with that one restriction, you're able to have all of the compiled work done, and still be able to cope with the fact that the length of the arrays and such like is not known until runtime.
Great. Thank you. I'm looking forward to looking at your work in some more detail. Do we have any more questions?
If you do have any...
Oh, yeah. Gunesh has a question too.
Hi. So this is all based on JVM, right? I was wondering if you compare your system to other JVM-based probabilistic programming systems, for example, Anglican, Enclosure.
In what sense? We haven't...
I mean, of course, I think I mean it in a runtime sense, or like maybe like the types of models that can be implemented, and like mainly like from a runtime point of view. Yeah.
So we haven't compared performance with other JVM-based languages at the moment. It's because this is still very much a work in progress. It feels a bit premature, because some places we're very fast compared to other things, and in other places where we've got optimizations that are still on the to-do list, you can end up with quite poor performance, and then go in and do a few simple optimizations by hand, which are things that the compiler should do and will do ultimately, and get 2 orders of magnitude performance increase. And so it feels that we'd be premature to do a comparison based on speed. The main goal, though, was about trying to make it easier for the people that we're running into in product groups to use probabilistic programming languages, because we've been a fan of them for quite a long time with things like the Argo work, but we kept running into people going, we don't want to put that in because it's going to confuse the hell out of everyone.
All right. Okay. Thank you.
Okay. Let's thank Daniel one more time.